Have you ever stopped to think about light? It's all around us all the time. It's the sunshine that warms your face, the glow from your phone screen, the twinkle of stars in the night sky. For most of history, we thought of light as just, well, light. It helped us see. A wave of energy that traveled incredibly fast. But what if I told you light has a secret identity? What if it could pretend to be something else entirely? Scientists are discovering that light is full of surprises. Under the right conditions, it can start to act like matter. Okay, let's talk about this strange word, quasiparticle. It sounds super complicated, but I promise it's an idea you can totally wrap your head around. Imagine you're at a crowded concert. If you look at one person, they are just an individual. But if you see a wave of people moving, that wave is a collective behavior. The wave itself isn't a person, right? It's a disturbance, a pattern that travels through the group. A quasiparticle is just like that. It's not a real particle, like an electron or a photon. It's a way to describe collective behavior of many particles acting together inside a material. Think of it another way. Picture a bubble rising through a glass of soda. Is the bubble a thing on its own? Not really. It's just a space where there's no soda. But we can still describe its properties, how fast it's rising, how big it is, and where it's going. We treat the bubble as if it were a particle, even though it's really the absence of liquid surrounded by interacting molecules. Quasiparticles are the physics equivalent, powerful shortcuts for understanding complex interactions. We usually think of light particles called photons as lone wolves. They zip through the vacuum of space at the speed of light, not really interacting with each other. If you shine two flashlight beams so they cross, the beams pass right through without a fuss. They don't bump. They don't stick. They don't form teams. This is because photons, by their nature, are antisocial. They are bosons. Many can occupy the same place at the same time. But they lack the interactions that let matter particles like electrons form complex structures. What if we could force those photons to mingle, create a special environment where they are forced to interact with their surroundings? This is exactly what scientists do, a kind of trap for light using layered semiconductors. When a photon enters, it gets caught up in the material's electrons. A rapid-fire game of tag. This creates something entirely new. The photon merges its identity with an excitation in the material. It's not just a photon anymore. Not just an electron excitation, it's a blend of both. It's a quasi-particle. This is the moment light starts to behave like matter. Because it's part matter, it inherits properties of matter. Suddenly, it has a tiny bit of mass, and these quasi-particles can interact. They can bump, repel, and influence one another, just like real particles of matter do. This is the fundamental trick. Dress a photon in a cloak of matter, and it gets a whole new personality. Let's give a name to our new friend, this hybrid particle of light and matter. Scientists call it a polariton. Isn't that a cool name? A polariton is born when a photon becomes strongly coupled with an exciton, an electron and a positively charged hole bound together. When a photon gets mixed up in this duo, they form a polariton, part light, part matter. From its photon side, it's incredibly lightweight and fast. From its matter side, it can interact. That ability to interact lets a collection behave like a fluid or even a solid. To create and study polaritons, scientists build microcavities, two mirrors nanometers apart with a thin semiconductor layer between. A photon of just the right color gets trapped, bouncing back and forth until it finds an exciton to form a stable polariton. Inside, they can create a dense gas of polaritons. Because they interact, it doesn't behave like a normal gas. Under the right conditions, they fall into the same quantum state, acting like a single giant superparticle. This is a Bose-Einstein condensate, or BE, a new state of light. It's a bizarre and wonderful phenomenon, and one of the most exciting frontiers in physics today. It's literally a new state of light. Once you have a collection of polaritons working as a Bose-Einstein condensate, things get really weird and wonderful. They stop acting like individuals and behave as a single unified quantum object. One stunning property is superfluidity, a fluid that can flow with zero friction or viscosity. Stir a cup of superfluid coffee, it would never stop swirling. Scientists have demonstrated this with polaritons inside microcavity devices. Side by side. Left, normal fluid turbulence. Right, polariton superfluid flowing smoothly around the obstacle. No ripples, no wake. A profound discovery, an exotic state predicted by Einstein, now seen in systems made of light. We can manipulate this fluid with lasers, change its density, and tune its flow with precision. This enables other phenomena, quantum vortices, tiny whirlpools that can only spin at specific, discrete speeds. By creating and observing vortices, scientists test deep predictions of quantum theory, tiny, controllable universes of light. We have quasi-particles of light that can act like matter and form superfluids. What can we do with them? Your devices push electrons through wires and silicon chips, generating heat, using lots of energy, and hitting speed limits. Engineers dream of computers that run on light. Optical computing promises to be faster and more energy efficient. But photons don't naturally interact. You can't build logic if one beam ignores another. This is where polaritons come to the rescue. Because they have a matter component, polaritons can interact. One stream of polaritons can control another, making light-based transistors possible. All optical logic gates and circuits could run incredibly fast. Wires become channels of light. Transistors become devices where one polariton stream switches another on or off. Because polaritons are lightweight with almost no resistance, especially as superfluids, circuits could be mind-bogglingly fast with little heat. This could power a new generation of supercomputers and revolutionize the internet's communication networks. Beyond classical computing, polaritons might help build quantum computers, harnessing superposition and entanglement. As intrinsic quantum hybrids of light and matter, polaritons could yield robust, controllable, and connectable qubits. While light-based quantum computers may be a few years away, the quasi-particle revolution is already paving the way for nearer tech. Your OLED screens and lasers rely on light matter control in semiconductors. Better understanding means better displays and smaller, more powerful lasers. Polaritons are delicately balanced, extremely sensitive to tiny changes in temperature, pressure, or single molecules. Sensors based on this could detect a single virus particle or a trace pollutant, revolutionizing medicine, monitoring, and security. Polaritons can form ultra-efficient lasers, big advances for manufacturing, surgery, and data communications. Ultimately, we're gaining fundamental control, designing materials with seemingly impossible properties, channel heat one way, or smart windows that switch using almost no energy. The quasi-particle concept is a new toolbox for building the future, one exotic, hybrid particle at a time. You might be thinking, superfluids of light and quantum computers sound cool, but what does this mean for my life? A century ago, the electron was a curiosity. No one imagined it would enable the entire digital world, the internet, and your video games. Quasi-particles are at that early, thrilling stage, pushing what's possible. It's about curiosity and discovery. Just as quantum mechanics led to lasers, transistors, and MRI, this research could seed the next technological leap. Students in school today will build these future technologies. Abstract science becomes tomorrow's engineering. Quasi-particles teach us to look for emergent patterns in biology, economics, and creativity. Sometimes you solve problems by redefining them. Even if you're not a physicist, understanding this makes you a more informed citizen, appreciating progress and its potential for clean energy, curing disease, and tackling big challenges. The story of light matter quasi-particles is a perfect example of what makes science amazing. It starts with a simple question: what if? What if light wasn't just light? What if it could team up with matter? Following that curiosity revealed new states of matter, showed light behaving in new ways, and inspired technologies that could reshape our future. You don't need a PhD. Ask questions, read about discoveries, try simple experiments. The world is filled with wonders for curious minds. The quasi-particle revolution shows there are secrets hiding in plain sight, even in a beam of light. The adventure is just getting started. Are you ready to join in?